Okay, so we, I believe, talked about concavity a little bit in pre-calculus. So concavity has to do with the curvature of our graph. Okay, so the types of concavity that you can have are concave upward and concave downward. So concave upward is going to be curved, up like this. And so it can look a few different ways. So whenever you are concave upward, you can either be decreasing at a decreasing rate. Okay, so you're going down, but it's the speed with which you are going down is slowing, right? So like you drop a bunch at first, and then a little bit, and a little bit, right? So this would be decreasing at a decreasing rate. This is going to be concave upward. So if you are decreasing at a decreasing rate, it's concave up. Increasing at an increasing rate is also concave upward. So you're increasing slow at first and then faster, right? So it'll look like this. You're going up, it's slow at first, but then it increases. So it gets steeper and steeper. Okay? Either of those are going to cause this like curved up look to your graph. Okay? Concave downward is like a sad face, right? And to look at the parts of that specifically, you could be increasing at a decreasing rate. So you're going up fast at first, but then it slows down. Or you could be decreasing at an increasing rate. So you're decreasing slowly at first, but then it drops faster and faster. Okay, so to think about this a little bit, this is going to deal with some derivatives because when we're talking about increasing at a decreasing rate. So increasing, we can tell by the sign of our derivative, right? We can tell if our derivative is positive, our function should be increasing. If our derivative is negative, our function should be decreasing. And then at a decreasing rate, what is the rate of change of the derivative? The second derivative, right? So if we take the derivative of our function, that gives us the slope or the rate of change of the tangent to that line. If we take the derivative of again, that gives us the rate of the rate, right? So that's what we'll be looking at here. So if a graph is concave upward, the slope of the tangent line increases from left to right. So just to think about, like an example, if we draw a picture here, our most simple concave upward graph would just be like a parabola, right? That parabola is concave up everywhere. So if you think of drawing in some tangent lines, like right here, you got a really steep negative tangent line. Let's call that like -5, right? Right here, it's not as negative. Maybe that's -1. Right here, you would have a tangent line of 0. Over here, now you're going to switch to a positive slope, maybe 1. Up here, you got a really steep tangent line, maybe 5, right? So if the graph is concave upward, the slope of the tangent line increases. So the slope of the tangent line, what do we use to represent the slope of the tangent line? That's first derivative, right? Slope of the tangent line is f prime. So if f prime is increasing, f has to be concave upward. Okay? Same thing's going to be true for concave down, but in the opposite manner, right? So if we look at this graph, like right here, we have a really steep positive. Maybe that's positive 5. Then right here, that slope maybe would be 1. Then here, we'd have 0. Then over here, we'd switch to a negative slope, maybe negative 1, negative 5. All right, so if a graph is concave down, the slope of the tangent line decreases from left to right. So that means that slope of the tangent line is f of x. So if we know, f prime of x, right? If we know that f prime of x is decreasing, then we know f would be concave down. So sometimes we will be asked to talk about concavity while looking at the first derivative. And we need to know whether that first derivative is positive or negative. Right, so we'll see some problems like this here in a minute. But sometimes we may not have like a graph of that first derivative. So how would we be able to tell if f prime of x is decreasing? Its derivative would be negative, right? So if f prime of x is decreasing, then its derivative is negative. The derivative of f prime is f double prime, right? So if f double prime is positive, that would tell us that f prime is increasing and that f is concave up. Or you can skip this middle part. If f double prime is positive, f is concave up. If f double prime is negative, that tells us f prime is decreasing and f is concave down. So we could even, if you kind of think about this in like a chart form, if we've got f of x, f prime of x, f double prime of x. So if I know that f is concave up, then I know that f prime would have to be increasing. And if f prime is increasing, that means its derivative must be positive. There. So for concave down, if my function is concave down, that means the derivative is decreasing. And if a function is decreasing, its derivative has to be negative. So the second derivative would be negative. So whenever you have problems for concavity, if you're given an equation like this, the easiest thing to do is to look at your second derivative. If your second derivative is positive, f of x will be concave up. If it is negative, you'll have the function being concave down. So the easiest thing to do here for this one in particular, because second derivative is really easy to find here, is to look at that second derivative. So f prime of x, Braden, what's f prime of x for this one? Okay, and then we need to look at the second derivative. Bo, what's my second derivative? Okay, so what we care about is the sign of the second derivative here. So a lot like we did when we were looking for relative maximum or minimums or increasing or decreasing, we want to look at the second derivative and make a sign line for that. So we want to know where this second derivative equals 0. These are not called critical points. Critical points are the zeros of your derivative. I have not came across anywhere that that the zeros of the second derivative really have a name that I've came across, and I've looked last year, I'm pretty sure. So sometimes we would just kind of like make up a name. So these are like really critical points or super second critical points or something, right? They're like critical points, but technically they're not, because that would only be for the first derivative. So we're going to set this equal to 0. We'll get 6x equals 18. We'll divide by 6. So x equals 3. That is the place where our second derivative equals 0. So we would make a chart. And actually, you don't really need a chart here, because your second derivative is just 6x minus 18, so there's not like multiple things to put on this chart. So if we plug in a number like 0 into our second derivative, will we get a positive or a negative? Negative. If we plug in a number like 4, what will we get? Positive over here. Okay? So much like your other problems, you are going to need to explain this. So you would say f of x is concave up on negative infinity to 3 because f double prime of x. Oh wait, I got that backwards, don't I? 3 to infinity. Let's fix that. Because f double prime of x is greater than 0 on this interval. And then we would say f of x is concave down on negative infinity to 3. Actually, I think they use brackets. I could be wrong about that. I need to go look on that. I know on increasing, decreasing. I need to look on concavity and see. I also am pretty sure that this is one of those things, like they're not actually going to count off if you get the brackets versus parentheses wrong. Because there is some debate, I believe. I guess I should put or equal to on this interval. So it's a lot like your increasing, decreasing, but you're looking at that second derivative. Okay. And if you have looked at your FRQs this week, they ask for points of inflection. And points of inflection are points where the concavity of the graph changes. So like this graph is going to have a point of inflection at 3 because your concavity changes there. I'm going to graph this original function here on Desmos real quick just so we can see what this looks like here. What was our original function? It was x to the third. So, equals x to the third. X to the second plus 24x minus 12. And so, if I put in x equals 3, actually, it splits our graph right here. You can see we're concave down right here, and then it switches to concave up. To me, it's really necessary to be able to use the derivative to find these. Maximum minimum points, when you're looking at a graph, you can a lot of times tell where they are at. So like I can tell that this maximum is at 2, 8 right here. But Points of inflection are a little harder to like see precisely where they happen because it can be really gradual. I know that it switches somewhere in here, but knowing that it's exactly at 3.6 is a little harder to know. So, be a little bit more important there. Yes. If you needed both, a lot of times you only need the x value. They'll just say find the x value of the points of inflection. But if they ask for the both coordinates, then you would just plug 3 into the original function. Okay, questions? All right, let's look at some more here. So we are supposed to determine the concavity of 6 times x squared plus 3 to the negative 1. So you could get rid of that negative exponent, but then you're going to have to use quotient rule. I would take the derivative like it is here. So when you take the derivative, Zach, what are we going to get when we take this derivative?
Negative 6 times x squared plus 3 to the power of negative 2 times 2x.
Very good. And then let's clean that up a little bit before we try to take the second derivative. So I've got negative 18. No. What's wrong with me today? Negative 12x times x squared plus 3 to the negative 2. That's my first derivative. Now, Zach got the easy one for that first derivative because here 6 is just a coefficient, right? So you don't have to use a product rule there. What have we got to do on the next one? Product rule, right? Because we've got a 12x, there's an x with this term now, times something else with an x. So you got to use a product rule here. So, Paul, when we try to take our second derivative, what are we going to get?
So, well, I just set it up.
Yeah.
So you have negative 12x times negative 2 over x squared plus 3 to the negative third power times 2x. And then it's plus x squared plus 3 to the negative 2 power. And then times negative 12.
Very good. Okay, so we're doing f times all of this stuff right here is g prime. You got to use the chain rule for that. And then g times our f prime there. So if we clean this up a little bit, because it is going to, I mean, you don't necessarily have to, but to be able to tell where this is 0 or undefined, it's going to be a lot easier if we simplify it. So I've got negative 12x, negative 2, and a 2x right here. So that's going to give me 24 times 2 will give me 48x squared times x squared plus 3 to the negative third. And then here I'm going to have, let me change that, plus to a minus 12 times x squared plus 3 to the negative 2. Now there's a couple ways that you can deal with this from this point, but what I would do is you've got these two pieces right here that match. So I would do what we've done before where we take out the lowest denominator there, which is that negative 3. So you are factoring out x squared plus 3 to the negative 3 power. If you want to take a 12 with it, you may. Yes. I think I'm going to hold off on that, but you can. So what we're doing there is it's like we're dividing by x squared plus 3 to the negative third from both of these because we're pulling it out. So it's just going to cancel on that first term, which means we'll just have our 48x squared. And then for our second term, x squared plus 3 to the negative third. What are you going to get there? I had a negative 2. I took negative 3 away. What? It is going to be minus 12 times x squared plus 3 just to the first power. Because if you think about, you got those negative exponents, you could switch where they're at. Then you would have x squared plus 3, right over here. You would have x squared plus 3 to the third would be on top. X squared plus 3 to the second would be on bottom. You would cancel 2 of those with this here, so you're just going to get the x squared plus 3 to the first power. And this usually happens when you factor out these negative exponent sort of things. You have one of them goes away completely, the other one just becomes a positive 1, in most cases anyway. So if I distribute here and simplify, I've got x squared plus 3 to the negative third. And then I've got 48 x squared minus 12x squared minus 36. And I'm going to go ahead and send the x squared plus 3 to the third down to the denominator. And I will get 36x squared minus 36. And if you want, you can write that as 36 times x squared minus 1 over x squared plus 3 cubed. It really doesn't matter. You can leave it either way. So all of this is my second derivative. You can see where these are more difficult because your derivative is just harder to find. The principle is the same as the beginning, but the derivative is more difficult to find. So to tell about concavity, we have got to look for places where the numerator or the denominator is 0. So we're setting both of these equal to 0. So for this, you got 36 times x squared minus 1 equals 0. The 36, I'm just going to divide off, it'll still be 0. So you'll get x squared minus 1 is 0. X squared equals 1. X is going to equal plus or minus 1. What's going to happen over here? X squared plus 3 equals 0. It's not going to be square root of 3, but if we cube root both sides, we got x squared plus 3 equals 0. We get x squared equals negative 3. And when you square root a negative, that's going to give you an imaginary number. Imaginary numbers are not going to give us any zeros, right? So you don't get anything out of this. If you think about what you've got here, you can notice it maybe even before you set that up. If you got x squared, that's going to be a positive number, right? Then you're adding 3 to it, which is still going to make it positive, and raising it to the third power, which is still positive, right? So there's no way that can ever equal 0. So you don't actually get anything from that denominator. So these can be a little exhausting. Negative 1, positive 1. I'm going to make a chart for this one. So I got 36. I got x squared minus 1. I've got x squared plus 3 to the third power. And I'm going to use all 3 of those there to find f double prime of x. So 36 is always positive. We also said x squared plus 3 cubed is also always positive. So actually all we care about is that x squared minus 1. If we plug in a number like negative 2 squared is 4. 4 minus 1 is 3. We will get a positive right here. If we plug in something like 0, 0 squared minus 1 would give me a negative, and then we'll get a positive over here. So we get positive, negative, positive. our second derivative. All right, questions? All right, so you got to conclude. So we would say f of x is concave up on negative infinity to negative 1 and 1 to infinity because f double prime of x is greater than 0 on this or these intervals. And then f of x is concave down on negative 1 to 1 because f double prime of x is less than or equal to 0 on this interval. Okay, questions here? All right. We might skip that one. Let's go to a trig one. This one, similar, it's just going, that second derivative takes you a little while to get on that one. And we're going to skip it because I want us to have plenty of time to go over the FRQ. All right, so here we've got one with trig, and we want to know where it is concave up. And we're only looking from 0 to 2 pi. So we need to look at second derivative. So thankfully, this is a pretty easy second derivative to find, as long as you know your trig derivatives. So Wesley, what would we get when we take the first derivative? Perfect. Okay. And then Serrata, what will we get for our second derivative? Okay. All right, so we care about where that second derivative equals 0, so we're going to set that equal to 0. And you can't really exactly solve this, but I could move the cosine over, so I've got sine x equals cosine x. So if we think about our unit circle, we need to think about where sine and cosine are equal, and where does that happen? Pi over 4. Right here, we got root 2 over 2 and root 2 over 2. And then where else? 5 pi over 4. No, they're both negative. There. So we're going to have x equals pi over 4 and 5 pi over 4 are going to be our sort of critical points. Not exactly critical points, right? So this is the second derivative. So if we look at, we're only looking from 0 to 2 pi, right? And we got pi over 4 here and 5 pi over 4, and we're going to be plugging into the second derivative. Is that all right with you guys if I write that second derivative as sine x minus cosine x, right? Instead of having the negative first, I just don't like it like that. So like if we pick a point between 0 and pi over 4, the only unit circle value we know there is pi over 6. So if I'm doing f double prime of pi over 6, I'm doing sine of pi over 6 minus cosine of pi over 6. And right here, we would have root 3 over 2, 1/2. Sine is your y coordinate, so you're going to have 1/2 minus root 3 over 2. Okay, is that going to give you positive or negative? It is negative because root 3 over 2 is bigger than 1/2. You don't have to know what it is, you just need to know whether it's positive or negative. Okay, between pi over 4 and 5 pi over 4, I would probably either pick pi over 2 or pi, just because I think they're easier. But you can pick anything that lies in this range right here. I think I'll use pi. So this is negative 1, 0 right here at pi. So if I do f double prime of pi, I'm going to have sine of pi. Sine of pi is our y coordinate, it's 0, minus cosine of pi, which is negative 1. And where I have that negative, negative, it will give me a positive 1. So I'll get positive here. And I'm going to bet that we get a negative for the next one, but you want to check just to be sure. I'd use 3 pi over 2, but you can use any value that falls in this domain right here. And so for 3 pi, f double prime of 3 pi over 2, this is 0, negative 1. So we're doing negative 1 minus 0, and that will give me negative 1, so we get negative here. Is everybody okay here? All right, what did it ask us for? Concave up. So we would conclude that f of x is concave up for pi over 4 to 5 pi over 4, because f double prime of x is greater than or equal to 0 on that interval. Okay, questions? This is really similar to increasing, decreasing. It's just you're looking at second derivative instead. Which makes, on ones like this, is not that bad. On the ones where the second derivative is hard to find, it can be extensive just because it takes a lot to find that second derivative. I guess we need to do these. They're not so bad. All right. So I've got f of x equals natural log of the square root of x squared plus 4. There is something we can do to this to make the derivative a lot easier on this before we start. So what if I write it this way? Natural log of x squared plus 4 to the 1/2. There was something special we could do with that exponent. What could we do? We could do chain rule, but that's not what makes this easy. It's properties of logs. It's back from pre-calculus. This exponent right here can be pulled out front as a coefficient. This only applies whenever you're dealing with logs. So this is not taking a derivative. This is just properties of logs tell us this exponent can come out front. So 1/2 natural log of x squared plus 4. By doing this, it makes it a lot easier to take the derivative because the 1/2 out here, it just stays out front as a coefficient. So when I take this first derivative, the 1/2 is just going to sort of stay out here. How do I do derivative of a natural log? 1 over whatever is on the inside, so that's x squared plus 4, times, we got to do chain rule here, so I'd multiply that by the derivative of x squared plus 4. What is that? 2x. It's like a 2x over 1. So this is going to give me this 2 right here can cancel with this 2 right here, so I will get x over x squared plus 4. It makes it a lot easier to pull that 1/2 out first, because otherwise you got like a chain rule that gets a little more extensive. That is only our first derivative. We must find the second derivative. So, let's see, Cade, what are we going to have to use to find the second derivative? Quotient rule. What's it going to look like for this one?
X squared plus 4 minus x minus 2x over x squared plus 4 squared.
Okay, very good. We did low times the derivative of the high, but the derivative of the high was just 1, minus high times the derivative of low, which was 2x, low squared. So if we simplify that a little bit, we got x squared plus 4 minus 2x squared. And that is going to give me 4 minus x squared over x squared plus 4 squared. And it's up to you. You can deal with this either way. You could even factor that top x plus 2 plus x, 2 minus x. Or you can leave it like it was. It doesn't matter. Okay, that wasn't too bad. That was an easy quotient rule at least. So we're going to set numerator and denominator equal to 0. So we will get x equals -2 and x equals +2. 0, 2, there. Right there. What about the denominator? If I have x squared plus 4, x squared is positive. Adding 4 to it makes it even more positive. Squaring it, still positive, right? That's never going to equal 0. If you set it equal and try to solve, you would square root both sides. X squared plus 4 would equal 0. You'd end up with x squared equals -4. And when you try to square root that, imaginary. So you don't get anything out of that denominator because it's always positive. So our sort of critical values that aren't called critical values for the second derivative. If I make a chart, I got 2 plus x, I got 2 minus x, and I got a x squared plus 4 squared. The reason I factored it is because I like to factor it for the chart. I think it makes it easier, but you don't have to do that. So this row right here is positive all the way across. That denominator is always positive. If I plug in a number like -3 here, I'd get a negative, then another negative, and then I'd get a, oh, is that true? That's false. If I plug in 0, I'd get a positive and then a positive here. And then if I plug in, be careful right here because it's kind of backwards. Usually they start with negatives and then switch to positives, but right here, if I plug in -3, I'd have 2 minus -3. Double negative makes it a positive. You actually get a positive right here. You would get positive if you plugged in something like 0, and then you get a negative over here. So we end up with negative, positive, negative. Okay, this one asked us for points of inflection, not concavity. So all the work leading up to it is the same. Your explanation is a little bit different. I like points of inflection a little better than relative max and min because you can make the general statement for both of them at the same time. So you have points of inflection at x equals -2 and 2. Let me take, give all x coordinates for point of inflection. We're going to change the word in here so we don't have to find the y coordinates here. Most of the time, you are only asked for x coordinates for these. Yes. Yes. Because there is a possibility. So there's a possibility that you don't change signs. So like if we had negative, positive, positive, then only -2 would be our point of inflection. So you do have to make this chart. Most of the time, all the critical values here are actually points of inflection because most of the time it just does alternate, but there are cases where it doesn't. So you do need to still make the chart and check.
Do you have to like say every single one of those, or like the denominator, not say that they count that? Doesn't matter.
The only thing you really have to do is this line right here. So I do the chart for my own personal benefit to figure it out faster. But if you are just doing it in your head without doing that, all you really need to state is like the signs of that second derivative. Because it would be perfectly fine to plug a number into the whole derivative without making that chart. So the chart is just a tool to do it a little bit faster. If you don't like it or need it, you don't have to use it. You just want to show this line right here where it says the second derivative. So you could leave that top part off if you wanted. All right, so we would say that f of x has points of inflection at x equals -2 and x equals 2 because f double prime of x changes signs at these points. You could say goes from negative to positive or positive to negative and like list them separate, but you don't have to. You can just say changes signs. For maximum minimums, it matters whether it's negative to positive or positive to negative because that tells us whether it is a maximum or a minimum. Points of inflection don't have special names for like going from concave up to concave down or down to up. So you can just put it in one blanket term there. All right, questions? All right, we got one more we're going to do. We need to do an E real quick. All right, so they're asking us where this function is concave down. So we need second derivative. I would start by rewriting this as e to the -2x to the -1. It is going to make it a little bit easier to take that derivative if you use negative exponents instead of doing -2 over x. So when we take the derivative of exponential, its derivative is the same, so e to the -2x to the -1. But then you must multiply by the derivative of the exponent because it's a chain rule there. So that, in this case, is going to be 2x to the -2. So if I want to clean that up a little bit, we got 2e -x to the -1 over x squared. Or if you want to leave it as it is, you can do a product rule. Do I want to just do product rule? Which one would be easier? Let's do product rule. Actually, I'm backing up. I'm going to leave it like it is. You could do that and do quotient, but let's try product. So this has two pieces to it. Both of those pieces have x's. So you need to use product rule. You could leave the two, you could move the 2 out front or leave it where it's at. It doesn't matter. So if you use product rule, you would have e to the negative 2x to the negative 1 times the derivative of 2x to the negative 2, which is going to be negative 4x to the negative 3rd, plus 2x to the negative 2 times the derivative of e to the negative 2x minus 1. We just did the derivative of e to the negative 2x minus 1. It was f prime of x, right? So that's going to be e to the negative 2x minus 1 times 2x to the negative 2. So we can see that both have these e to the negative 2x to the negative 1. I'm going to move that out front, factor it out. E to the negative 2x to the negative 1. And so this is going to give us negative 4x to the negative 3rd plus, right here I've got 2x to the negative 2 and 2x to the negative 2, which could give me 4x to the negative 4. Let's see what's going to be the easiest way to deal with that. Probably to get rid of all those negative exponents. So I can write this as 1 over e to the 2 over x. So that negative right there with the 2 moves this to the bottom, and I went ahead and did that negative x. I moved it to the bottom of that fraction. And then over here I'd have negative 4 over x cubed plus 4 over x to the 4th. Let's stop for a second, save everybody. Is everybody good here? Probably common denominators right here. So if I multiply by x on top and bottom here, I'm going to get negative 4x plus 4 over, I'll have the e to the 2 over x and the x to the 4th here. And so for this, we want to know where numerator and denominator are equal to 0. And so we'll have negative 4x plus 4 equals 0. That's going to be 4 equals 4x. So we get 1 there. What about e to the negative 2x, or 2 over x equaling 0? It would not exist because e's to any power are always positive. So, like what I'd have to do here is I'd have to take natural logs of both sides to get rid of that e, but natural log of 0 does not exist. So you don't get an answer from that. E to any power is going to be positive for you. And then you'll have x to the 4th equals 0. That's just going to be x equals 0. So, this one's wilder than it looked at first. So, I've got negative 4x plus 4. I've got e to the 2 over x, and I've got x to the 4th. And I will use those three to find my f double prime of x. So the E line is positive all the way across. For this top line, if I plugged in something like -1, -4 times -1 would become positive, so I'll get a positive right there. Something between 0 and 1, like 1/2, -4 times 1/2 would be -2, plus 4, still positive here, but we'll get a negative on the end there. And for x to the 4th, actually x to the 4th, what are we going to get for it? Also positive all the way across, because if you raise something to the 4th power, it's going to be positive, because it's an even power. So you actually end up with plus, plus, minus here. So, Bo, this is sort of like an answer to your question here. We found 2 critical points, but the only point of inflection is actually at 1. This one was asking us for concave down, so we don't have to talk about points of inflection. But we would say that f of x is concave down on 1 to infinity because f double prime of x is less than or equal to 0 on this interval. Alright, so questions about any of this? Alright, let me see if that, I think what I put in Canvas is different than that. Let me see. No, it's the same. Let me see, because let me see what those look like. I think some of them are a little bit easier than others. Alright, let's see. Alright, 3's easy. 6 is difficult. 10 is difficult. 13's easy. 18's a little difficult. Alright, let's see. This is a little much. So, I don't think I need to give you 6. If you can do 10, you can do 6. And we'll take out 11. 13's easy. We'll take out 18. If you can do 19, you can do 18. And 28 is actually pretty easy. And 31. Yeah, that's what. Okay, I've got to leave those. That gives us what? 1, 2, 3, 4, 5, 6. That gets down to a little more reasonable workload there. Let me take that off of Canvas also. I'll take out 6, 11, 18. If you want to do 6, 11, and 18, they are good problems for you to practice. I just don't want you to spend an hour and a half on homework tonight. So, we do need to look at our free response questions. So you guys have a couple for this week because we'll have our quiz tomorrow. Pull that up. It's week 9, right? which one do you guys want to look at? I would say they're both probably pretty equally difficult here. So which one would you guys like to do? One? Okay, let's look at one. Alright, so, make sure I'm still recording. Alright, so, for this one, it says let f be the function defined by f of x equals k square root of x minus natural log of x. And we know x is greater than 0 and k is a positive constant. So they ask us to find f prime of x and f double prime of x. So we have a k that is a positive constant, but we don't know what it is. I would write it like this: f of x equals k x to the 1/2 minus natural log of x first. Alright, so if I take the derivative of this, I'm going to get 1/2 kx to the negative 1/2. And then what's the derivative of natural log of x? 1 over x. Okay, so that's my first derivative. I may want to take the second derivative. I may want to write this as x to the negative 1 power. Just makes it a little bit easier because you don't have to use a quotient rule there. So this is f prime of x. And they also ask us for second derivative, so we're just going to do that power rule one more time. So we'll get negative 1/4 kx to the negative 3/2 plus x to the negative 2. I did not have to use a product rule right here because k is just a coefficient. K is like a 3 or a 7 or a 2. We don't know what it is, but it's just a positive number. If k was actually a variable, then we would have to use a product rule, but we don't. So, it might be helpful later on for us to simplify this or change something, but right now there's no necessity to do that. So I would just leave it with negative exponents. I would leave it like it is, because as it is, you don't have to worry about, making a mistake whenever you do that. Let me see if I did that on my key. Yeah. Okay. So, we all okay here? This part's pretty straightforward, as long as you recognize that k is a coefficient. So that's probably going to be worth 2 points, I think, a point for f prime and a point for f double prime. It says, for what value of the constant k does f have a critical point at x equals 1? For this value of k, determine whether f has a relative minimum, relative maximum, or neither at x equals 1, and justify your answer. All right, so there's a lot of things you have to reason through here. So we're looking where f has a critical point at x equals 1. What happens at our critical point? Our slope, or our derivative, f prime of x, is going to equal 0 or undefined. But I think probably 0 is what we're going to need to worry about. So if I take this first derivative right here, I can set it equal to 0. And we know the critical point is going to be at x equals 1. So we can also go ahead and plug in 1 for our x. So I got 0 equals 1/2 times k times 1 to the negative 1/2 minus 1 over 1. What is 1 to any power? 1. So this is just going to be 0 equals 1/2 k minus 1. So we could add 1 to both sides. 1 equals 1/2 k. And then you could either multiply by 2 or divide by 1/2. Either way, you're going to get 2 for your k. So at this point, I would plug in 2 for my k. So I know that f prime of x is going to equal 1/2 times 2x to the negative 1/2 minus 1 over x, which means f prime of x is just going to be x to the negative 1/2 minus 1 over x, and I think I'll write it like this: 1 over the square root of x minus 1 over x. Now, what point are they asking us about? Are they asking us to find all relative maximum minimums? Just at 1. So my question, do we need to find other critical values? Maybe. We might need to, because otherwise our chart, like we might pick a number below 1 to plug in that actually is like outside of our range. So I think we do still need to find our other critical values. So it'll be easier to do if you have common denominators here. So if you multiply this by square root of x on top and bottom, you'll get square root of x minus 1 over x. So in the top, square root of x minus 1 equals 0. That's just going to be x equals 1 when you solve it. And in the bottom, you'll get x equals 0. And so I didn't let myself enough room for a chart. We'll just plug in. So we know, I think the problem tells us that x has to be greater than 0, so we don't need to test anything down here. Plus, we only care about 1, so we just care about either side of 1. So if I plug in like 1/2 is not a great thing to plug in, because 1/2 I can't take the square root of. Although I do know, I mean, if I do plug in 1/2, I've got square root of 1/2 minus 1 over 1/2. Square root of 1/2 is less than 1, so I got a negative over a positive, which gives me negative. But if you want to get an actual number, 1/4 is better, because 1/4 you can actually take the square root of. And then a number bigger than 1, you could plug in 2. It's fine if you plug in 2. Square root of 2 minus 1 over 2. Square root of 2 is bigger than 1, so you get a positive over a positive, and you get a positive here. But if you plug in something like square root of 4 or 9 or 16, you can actually get the whole number if you want. So since we see our derivative switch from negative to positive, we have a relative minimum here. So we would say that f has a relative minimum at x equals 1 since f prime of x switches from negative to positive at x equals 1, or at that point. For this particular question, it just says for this value of k, determine whether f has a minimum, relative maximum, or neither at x equals 1. So they're only asking about x equals 1, so you don't have, the only reason that I did make sure I went ahead and found 0 is because, like, let's say that you had a critical point at 1/2, then it would make a difference what number you plugged in. So, like, if there was a critical point at 1/2 and you plugged in like 1/4, it might look like it was positive, but it really wasn't. So that's the only reason you kind of need to find it here. But you only have to explain whether it's maximum or minimum at 1 because they only asked for it on this problem. Now, if they asked you to find all critical points and determine whether there's a maximum minimum, or then you would need to talk about it. In this particular case, because the function is not defined for 0, you wouldn't have anything there because the function is not defined. Okay, questions on that? All right, so for a certain value of k, of the constant k, the graph of f has a point of inflection on the x-axis. Find this value of k. So there's several things we've got to think about here. Let me glance at my key just to make sure I'm going to be. Let's see. Okay, yeah. All right. So, this is a tricky problem. So, point of inflection. So, when we're looking at a point of inflection, what has to be true at our point of inflection? We're concave up to concave down, which means double prime changes from positive to negative or vice versa, right? And for double prime to change, we would have to have the second derivative has to be equal to 0, right? Because our second, or undefined, because our second derivative can't change signs without either being 0 or undefined at that point. Okay? What does it tell us that something is on the x-axis? Not x equals 0. Y equals 0. So we've got two pieces of information here from this. Also, be careful in this. They are not telling you to use what you found in B. K is not 2. You cannot plug in 2 for your K. This is a separate situation, right? So we can either set the second derivative equal to 0 or undefined, or we can set y equal to 0 in the original function, right? Or we might need to do both. I'm going to try this y equals 0 in the original function and see if it gets us anywhere. So if I do, my original function was f of x equals k square root of x minus natural log of x. And so that's 0 equals k square root of x minus natural log of x. And I really can't solve that for x, really. Not easily, anyway. So let's go over to second derivative equaling 0. Let's see if that'll get us anywhere. So second derivative was negative 1/4 kx to negative 3/2. Plus x to the negative 2 equals 0. So I'm going to write this back. This would be negative k over 4 square root of x cubed plus 1 over x equals 0. I could move the, yes, thank you. I could move this stuff over to the other side, which would give me 1 over x squared equals negative k over 4 square root of x to the third. Cross multiply negative kx squared 4 square root of x to the third. Yes, oh thank you. Yes, it should. So it should be a positive k right there. Alright. Oh gosh, I'm going to have to look back at my... Okay. Let's look back at my key. Oh, I got, yeah. Alright, so if I solve this for k, I cannot solve for x, but I could solve for k. So divide by x squared, divide by x squared. K equals, this is x to the 3/2, and then that's x squared, so that's going to give us 4 over x to the 1/2, or 4 over square root of x, because what you're doing there is you got 4x to the 3/2 over x to the second, so if you subtract those, you get 1/2 and keep it in the bottom. Solve both for. Right, they both equal k, so we can set them equal to each other. 4 over square root of x equals natural log of x over square root of x. Since they're both over the square root of x, those essentially just cancel out, right? And you just have 4 equals the natural log of x. How do you get rid of natural log? E to the power. So x is e to the 4th. But it didn't ask us for x. What did it ask for? It asked us for k. So you can plug k into either, or plug x into either one of these functions. So you could plug it in here, or you could plug it in here. And then, so k would be 4 over square root of e to the 4th, which is 4 over e squared. And that would be your answer. And that is the answer I got on my key, isn't it? I hope. Yeah. So that one is difficult. If it shows up to, if it ends up being this one, remember you got y equals 0, you got f double prime equals 0. Solve both of those equations for k and set them equal for that. All right, so you've got those problems for concavity tonight, and then make sure you have your FRQs ready. I do have smart breakfast in the morning if you have any questions about anything for those. Question, Raven? I plugged it in. You can plug it into either one of these equations for K. I just used this one because it looked more simple to me. So I got 4 over e squared. If you plug it in over here, you got natural log of e to the 4th over the square root of e to the 4th. And so natural log and e's cancel. It's just giving you 4 in the top, and then you'll get an e squared in the bottom there also. Yeah. And technically you could leave it here. You don't have to simplify it. Or you could even leave it here, there. But yeah, so either one should give you the same thing.